Hello friends, welcome to my lecture series on digital signal processing. In previous lecture, we discussed Fourier transform and its important properties. In this lecture, we are going to address a very important theorem called sampling theorem. Basically, it is a gateway which enables the processing of signals in discrete time domain, also called digital signal processing. The sampling theorem states that any band-limited analog signal x of t can be recovered from its sampled version if and only if sampling frequency is greater than or equal to twice the maximum frequency of analog signal. Here, the important requirement for sampling theorem to satisfy is x of t should be band-limited. So consider signal x of t, assuming it is a band limited, having Fourier transform such that x of t is a transformable to x of omega. It is band limited to the maximum frequency omega n, which is sampled at a uniform time interval Ts using train of impulses, which in turn generates a sampled version of analog signal as shown by the dotted line. The sampled signal is represented as xst or x of t with subscript s, and that is equal to product of x of t with sampling signal s of t, and that will become x of nts, which is also written as a x of n because the sampling interval Ts is constant. Since s of t is a periodic signal, as we know, we can represent it by means of a Fourier series. So here we are using a complex form of the Fourier series. S of t is equal to summation n is varying from minus infinity to plus infinity Cn into e raised to jn omega s t, where omega s is a sampling frequency. Now where Cn is given by 1 by t integral of s of t into e raised to minus jn omega st dt, where limits of integrations are from minus t by 2 to plus t by 2, where t is a sampling interval. Now here the question is, what is the frequency spectrum of discrete time signal which is obtained after sampling of analog signal? If one can obtain the spectrum of discrete time signal, it will give the answer for the sampling theorem. That is, what is the requirement to recover analog signal from its discrete time version, assuming signal is band limited. So here, first of all, we'll find out the Fourier transform, that is a spectrum of x of omega with subscript s, that implies xs omega is a Fourier transform of xs t. So here the process is pretty straightforward. First we'll calculate the Cn, and that is equal to 1 by Ts integral of delta t into e raised to minus jn omega st dt. Here we are applying Fourier series to s of t, and if you consider the period which is minus Ts by 2 to plus Ts by 2, then there exists only one impulse, which is a delta t, and therefore Cn can be computed by simplified equation where the product delta t into e raised to minus jn omega st will exist only at t equal to 0, which makes e raised to 0 equal to 1, and hence the area under the impulse is 1, which gives Cn equal to 1 by Ts. Now once we got value for Cn, then we can compute the Fourier transform of sampled version of the signal as xs omega equal to Fourier transform of xs t, that is Fourier transform of x of t into s of t. By substituting s of t as a Fourier series and substituting value of Cn, which is 1 by Ts, you'll get a simplified equation for the Fourier transform of sampled version of analog signal as excess of omega is equal to 1 by Ts Fourier transform of summation n is varying from minus infinity to plus infinity x of t into e raised to jn omega st. Now here we have shifted x of t inside the summation. Technically it is a constant as far as summation is concerned because summation is with respect to n and x of t is independent of n. However, we are shifting it inside because the Fourier transform is an integration with respect to time and summation is with respect to n, and hence we can change the order of operation. Now we can compute the Fourier transform of x of t into e raised to jn omega s t, and here we can apply the modulation property which we already studied in our previous lecture, and therefore it will become x of omega minus n omega s. So when this Fourier transform of x of t into e raised to jn omega s t is substituted, you will get the final equation for Fourier transform of discrete time signal xst, which is nothing but xs omega equal to 1 upon ts summation n is varying from minus infinity to plus infinity x of omega minus n omega s. Even though this equation look slightly complex, conceptually it is pretty straightforward equation. So here try to understand the terms. X of omega is a Fourier transform of original analog signal, that is x of t, and that is shifted by amount n omega s, and then for various value of n, the shifted version of the spectrum by amount 1 omega s, 2 omega s, 3 omega s on both the side are accumulated to form the spectrum of discrete time signal xst, and hence it is a periodic version of x of omega which repeat itself at omega s, 2 omega s and so on, as shown in the spectrum of xs omega. So this is a xs omega for n equal to 0, which is nothing but x of omega only. When n is equal to 1, it will become x of omega minus omega s. So x of omega will repeat itself at omega s. When n is equal to minus 1, then xs omega will become x of omega plus omega s, which means x of omega will reproduce at minus omega s, and it will continue up to infinity because n varies from minus infinity to plus infinity. So the spectrum of discrete time signal is nothing different except it becomes a periodic version of original analog signal. Now here we can recover an analog signal if we can recover the spectrum of original analog signal from the spectrum of sampled version of the signal, and that is possible by filtering the original spectrum from xs omega and rejecting side spectrum of xs omega. So here we are showing an ideal filter in the red color, assuming ideal filter exists, and then practical filter will solve the problem very soon. Now here the width of main lobe is Wm because it is a band limited signal, and then one can figure it out. The width 0 to omega s should be greater than twice omega m in order to avoid overlapping of adjacent spectrum, so that ideal filter can filter the original spectrum of analog signal. Now here, if you avoid overlapping of adjacent spectrum, then the condition required is there has to have a gap between two adjacent spectrum, and that is possible only when omega s is greater than twice omega m. And when you convert omega into linear frequency, which will give fs should be greater than or equal to twice fm. And that is a proof of sampling theorem. So any band limited signal can be recovered from its sampled version if and only if sampling frequency is greater than or equal to twice the maximum frequency of an analog signal. Now here one question is there: if signal is not band limited, that is if signal is band unlimited, then how one can sample the analog signal? So answer is pretty straightforward. Just pass it through a low pass filter with cutoff frequency omega m, and it can be converted into a band limited signal. Now we'll see some important aspects of sampling theorem. Practically, we cannot design an ideal filter. So the real life low pass filter will have a finite slope, and that finite slope will overlap if gap is exactly 0. That is omega s is equal to exactly twice omega m. So in order to design a practical low pass filter, in the process of recovering analog signal from its discrete time signal, we have to have some gap in adjacent spectrum of sampled version of analog signal or discrete time signal, which is called the guard band, and practically it is kept around 20 to 25% in order to simplify the design of practical filter, as shown by this dotted blue color line. Now we'll see the important aspects of sampling theorem. So here in nutshell, fs should be greater than or equal to twice fm for a band limited signal, assuming x of t is transformable to x of omega. Then the spectrum of sampled version of analog signal is nothing but the periodic version of x of omega, which repeats itself at n omega s, where n is varying from minus infinity to plus infinity. It may cause a frequency aliasing if sampling frequency is less than twice fm. In that case, the adjacent spectrum will overlap and it will result in a noise whenever signal is reconstructed using low pass filter, and that has to be eliminated. So if signal is not band limited, pass it through a low pass filter with cutoff frequency omega m, and one can avoid the frequency aliasing, and that will at the end will avoid noise generated in the output signal. Now we'll see another aspect, that is a real-time system. So whenever you sample an analog signal at a sampling frequency fs, and then it is processed using a linear time invariant system in discrete time domain, and therefore it is called discrete time system, and generates the output y of n. Then for real-time system, the output should also arrive at sampling frequency fs, unless and until there is no change in the sampling frequency. For example, if you are processing a signal at say 50 kilohertz samples per second, then one should finish the processing of 50,000 samples in 1 second. And if system is processing the signal at that rate, then it is called a real-time system. Now we'll see another important concept, which is MIPS. That is, if your system is operating at sampling frequency fs, then how many MIPS are required on your embedded system? Now here consider various parameters. fs is samples per second, which is a sampling frequency. B is a block of samples at the output of the algorithm. K is the instruction for a block of samples, which means you need k instructions in an algorithm to finish processing of B samples of algorithm. For example, if you are having a FFT algorithm which generates 1000 frequency beams for 1000 sample input, then the block size is 1000. And one can find out how many instructions are required to implement FFT algorithm by reviewing the code. And once you get number of instructions per block of samples, you can calculate instructions per sample as n equal to k by b. Now t is the time of algorithm, but which can be computed by profiling your software code. And then the MIPS are defined as million instructions per second, which is equal to n into fs, where n is instructions per cycle multiplied by sampling frequency, which is nothing but samples per second. So samples will get cancelled and you'll get instructions per sample divided by 10 raised to 6, which will give the million instructions per sample, where n can be substituted as k by b. So this is a formulation for computing the MIPS requirement of your algorithm, and it shows that it depends on your fs. So as your sampling frequency increases, your MIPS requirement, that is a compute power requirement of an algorithm, also increases, which is quite obvious. For example, suppose your sampling frequency is 50 kilohertz. That is, you are generating 50,000 samples per second. And when you compare with another system where sampling frequency is 100 kilohertz, it means you are generating 100k samples per second. So obviously you'll need double the time to process 100k samples per second compared to 50,000 samples per second. And hence, whenever you are operating your algorithm at higher sampling frequency, it will demand more compute power from your processor. Now here, for a system to be a real-time system, then B by T, that is number of samples generated by algorithm in time T, should be greater than Fs, because Fs is a sampling frequency at which samples are generated. So it is always expected that your algorithm finishes the job processing of that many samples in a shorter time compared to Ts, and which will give the requirement for a real-time system to be B by T should be greater than or equal to Fs, where T is the time of the algorithm. Now there is another important concept if you want to study the real-time system and the power consumption in the real-time system, which is a very important factor, because in most of the embedded system which are operating on the battery, so here as clock frequency increases, because of the compute power requirement of algorithm increases because of sampling frequency, then the power consumption in your system also increases, which drains more battery, and hence your battery drainage becomes faster and you have to charge your battery frequently, which is not a good feature in most of the embedded system like a mobile phone. Now here consider you are having a processor which is clocked at say 1 gigahertz frequency. Typically nowadays a processor execute one instruction per cycle. So here whenever processor is operating at 1 gigahertz, it means it gives you 1 GIPS, that is a 1 giga instructions per second. So that much compute capabilities available from processor side. Now you have to find out compute capability required for an algorithm. And in order to make system to be a real time, the compute power of processor should be greater than or equal to compute power requirement of an algorithm. So here, if you are operating your algorithm at higher sampling frequency, it will demand more MIPS, and more MIPS will demand higher clocking rate. Higher clocking rate demands higher power consumption because of the CMOS logic of VLSI circuit, which will drain more power, and that will heat up your system and it will drain your battery quite faster, which is not a good feature. So one has to optimize the algorithm by reducing the MIPS requirement on any embedded platform which uses a DSP or a GPU or some embedded processor. I think you must have enjoyed my lecture on this sampling theorem, and thank you for your patience and watching my show.